Okay, good morning, everyone. So welcome back to the third lesson in the round 2 training for the Junior Chemistry Olympiad. Now, this lesson, we will focus on organic reaction mechanisms. Okay, so in secondary school, we usually learn the reactions. For example, we learn that alkanes undergo substitution with chlorine in the presence of ultraviolet light. Alkenes undergo addition, right? And so on and so forth. So in secondary school, we focus on the type of reactions. We do not focus on exactly how the reactions work. So today, we're going to extend that understanding by understanding how reactions work. So mechanism refers to how reactions work. Now, specifically, how do all chemical reactions work? All chemical reactions work based on how the electrons move around. So if you think back to chemical bonding, you learned ionic bonding, right? So ions are formed when the metal atom loses valence electrons. The non-metal atom gains valence electrons, right? So there's a loss, there's a gain of valence electrons. Or you can have covalent bonding, where covalent bonds are formed through the sharing of valence electrons. So the idea behind every single type of reaction is we form bonds, we break bonds, and this involves the movement of electrons. All right, so how do electrons move around and how bonds are broken and formed? So under energy changes, you learned how to calculate the delta H, the enthalpy change of a reaction. And that is based on what bonds are broken and formed, how many of these bonds are broken and formed, and what is the strength of these bonds, right? So delta H is not simply the number of bonds broken and formed. It is the amount of energy taken in to break the bonds relative compared to the amount of energy released in forming the bonds. All right. So the mechanism of a reaction will show us how the electrons move around and which bonds are broken and formed. And the way we do this is that we will use arrows to indicate movement of electrons. Okay, so today we will be drawing a lot of arrows. Whenever you draw an arrow, what you mean is that the electrons are moving in a particular direction, a particular way. All right, so I will explain more using the examples of free radical substitution and electrophilic addition later on. All right, but the idea is today you'll be drawing loads of arrows. And this is why the reaction mechanism in organic chemistry is also called the curly arrow mechanisms, because we are using arrows to indicate movement of electrons. Okay, now we'll be starting our first mechanism, which is called free radical substitution. Okay, you have heard of substitution before. You have heard, okay, free radical substitution. You have heard of the word substitution before. Substitution is a type of reaction that alkanes undergo. All right. So one example of this reaction is alkanes reacting with chlorine gas in UV light. This is an example of a substitution reaction. So today we will learn how to draw the mechanism for this reaction of alkane plus chlorine. Okay? Now, free radical substitution is the mechanism for alkanes plus chlorine. There are a number of steps. The first step is called initiation. So initiation is the first step of the mechanism. And in this first step, what happens is that the chlorine-chlorine covalent bond. So this is the covalent bond present in Cl2, right? What happens is the covalent bond breaks. Now, please follow my arrows. you notice that my arrows are single-headed. Okay, the arrows are single-headed. We can also call them half arrows. Okay, now whenever you have half arrows like what I have drawn and highlighted to you in yellow, this signifies the covalent bond breaks and the electrons in the bond are given evenly to each atom. So if you think about it, how many electrons are there in the bond that is being shared? So the Cl-Cl covalent bond has 2 electrons being shared, right? Remember we said this under covalent bonding. Each chlorine atom shares 1 valence electron with the other chlorine atom to form a molecule of Cl2. So this covalent bond has a total of 2 shared electrons. So at the end of the reaction, what you have, each chlorine atom gets 1 electron back from the bond. So each Cl atom gets 1 of the shared electrons. Okay? Can? So this is the idea. Okay, this is the initiation step. Right? Okay, so at the end of initiation, we get 2 chlorine atoms. Now, these chlorine atoms have an odd number of electrons. Okay, they have an unpaired electron. As you can see, the electron that's indicated with a dot, that's not paired, right? So this is called a chlorine free radical. All right, and free radicals are very, very reactive. Okay. Now, this bond breaking in the initiation step, you are breaking the Cl-Cl covalent bond. It has to take in energy from the surroundings. So the initiation step is endothermic. It takes in energy from the surroundings because it's bond breaking. Now, what is the form of energy supplied to this reaction? So obviously we know by now, the form of energy supplied to this reaction is actually in the form of ultraviolet light. So the bond breaking of the Cl-Cl covalent bond occurs in the presence of ultraviolet light. Okay. Now, this breaking is a single-headed half arrow. So the electrons are given evenly, and it forms a radical at the end. So you must link these things together. Whenever you see half arrows, you know the electrons in the covalent bond have been given equally back to each atom in the bond. Therefore, what you get is a radical with a dot like that. Okay, now this has a name. This is called homolytic fission. Of the Cl-Cl covalent bond. Homolytic fission means the electrons are given equally, evenly back to each atom. Okay. So after initiation is done, initiation is the starting, right? It needs to start reacting with the alkane. So that is the propagation step. Propagation means how the reaction continues from here. So we already said in initiation, we have produced the chlorine free radical, which is very, very reactive. So now, if I were to have a methane molecule, CH4 is methane. Okay, and I have a Cl dot, a chlorine free radical. What happens? Okay, so what happens is this. First, one of the CH bonds will break. Okay, let me draw the arrows neatly. But when the CH bond breaks, it doesn't form H radical. The H radical is immediately captured by a Cl. So we usually draw the arrow to go in between the H and the Cl. This signifies a new HCl bond is formed. And what you get at the end is this. Now the radical is on the carbon plus a new HCl molecule, which we know is present. In free radical substitution of alkanes with chlorine, you produce HCl. Okay? So take note of how the arrows and where the arrows are placed. The arrow is deliberately placed between H and Cl. This signifies to you that a new HCl covalent bond is formed during the process. Now, obviously, the CH3 with a dot, this is called methyl radical. Again, radicals are reactive. You know this is not going to stay for too long. So what will the CH3 dot do? So the CH3 dot, look at it. Okay, it will produce and it will react with another molecule of chlorine. Okay, how? Again, it can form a new bond with chlorine, right? So this signifies that you are forming a CCl covalent bond. So can you see I've placed the arrows in a very distinct, very specific position in between the carbon and the chlorine. So this tells you that, okay, the electrons are going to be shared between carbon and chlorine. Therefore, a new carbon-chlorine covalent bond is formed, which is correct because we know the free radical substitution should result in the formation of this molecule, okay, chloromethane. But if you look at this arrow, oops, sorry. If you look at this arrow that's highlighted in blue, what do you form from it? Remember, it's a single-headed half arrow. You will form another chlorine radical. Okay, so in addition to chloromethane, you will form another chlorine-free radical. So now let's take a look. Oops. The chlorine-free radical is used up in the first step of propagation, but formed or regenerated again in the second step of propagation. So this should sound familiar to you. We have seen similar situations before where something is used up in the first step and formed back in the second step. Okay, now this means that the reactions will continue on and on and on and on. So this leads to a chain reaction. That means the reaction continues until all the Cl2 or methane, the alkane, is used up. Okay. Now you might be wondering, does that mean that chlorine radicals are the catalyst for the reaction? Now, whether it's a catalyst or not, yes, catalysts are used up in the first step and form back in the second step. However, you also need to consider this is just one part of the whole mechanism, right? We are not at the end of the mechanism yet. You got to consider at the end of the reaction is Cl used up. Okay, you can't just look at one part of the mechanism. You got to look at the whole mechanism. If you look at the whole mechanism later on, we will go through, you will realize the chlorine radicals are used up at the end, which means that it is incorrect to say that chlorine radicals are a catalyst. They are not a catalyst. Okay, so remember, yes, catalysts are used up and regenerated again. However, you need to look at the overall whole mechanism. So in this case, in this particular case, chlorine is not a catalyst, okay? And we will now see why when we go on to termination, which is the last part of this mechanism, okay? So the last step of this mechanism is termination, where the reaction stops, the reaction terminates. Now, radicals are very reactive. So if the radicals continue to exist, the reaction doesn't stop. So termination always involves the collision and reaction of two radicals. So now you got to think, what are the radicals that you have seen so far? You have seen this, right? You have seen chlorine radicals so far in this mechanism. So what happens is that the electrons can come back together. Do you realize my arrows? The electrons come back to each other to be shared. So this forms Cl2 again. All right. Now another radical, of course, just now we saw is the methyl, CH3 dot and Cl dot. So again, they can come back together. Okay, make sure you draw a single-headed half arrow. All right. So again, they come back together, and this you can tell forms a CCl covalent bond. Okay, and the reaction stops here, of course, because okay, it doesn't form any more radicals. Finally, another less common product. What is stopping two CH3 radicals from coming together? They are reactive, they can come together. So what is formed? If two CH3 come together, they form C2H6. Right? So the new covalent bond form is this. So they form ethane. But this is a small amount. Okay, so actually the free radical substitution of methane does form a little bit of ethane as a byproduct. A little bit, not a lot, a little bit. Okay, so the idea behind termination is that the radicals must collide and react. Therefore, the reaction will stop because it's the radicals which are very reactive that are powering the reaction forward. They are propagating the reaction. Okay. Now, of course, we have learned, will the reaction simply stop at one chlorine being substituted? Okay, it may not, right? So this product, chloromethane, this product could potentially go on to substitute away more hydrogen, right? So we already know this, especially when you have excess Cl2. When you have excess Cl2, the tendency is for multiple substitution to happen, meaning more of the H goes out, more Cl comes in. So it may not stop here also. It could potentially go on. How to potentially go on? The mechanism is the same as this. It has to go through the initiation, the propagation, and termination again. All right? Now, all this obviously happens at a microscopic scale. So scientists knew about this mechanism through testing. We are able to test and detect the radicals as the intermediates for the reaction. That's the reason why we know the mechanism is as such. Now, you notice the only radicals we have are the chlorine and the methyl radical. We do not have any free hydrogen radicals. There's no hydrogen radical. There's no H dot. Okay? Never don't have any H dot in the free radical substitution mechanism. Okay? Now, this is the mechanism called free radical substitution, which applies to alkanes reacting with chlorine gas in ultraviolet light. Okay, we have used methane, CH4, as an alkane, as an example of alkane, because that's the smallest, simplest. Okay, but all the other alkanes will follow the same steps. We just need to customize the structures of the radicals formed. Okay. Okay, so now we have seen the mechanism for the reaction of methane with chlorine. But what if we used a more complicated alkane that is not symmetrical? For example, now, what if we use propane plus chlorine? Now, propane has 3 carbon atoms. So if you recall, pro means 3 carbon. So this is the structure of propane, which is C3H8. All right. Now, usually we will not draw propane as such. Okay, for longer molecules, instead of drawing all the C and H out, we will use what we call the skeletal formula. So at O level, you learn the full structural formula. But more commonly in organic chemistry textbooks at higher level, we will use a skeletal formula. Skeletal formula is where propane is just represented like this. All right. Now, how do we work this out? Basically, every single vertex of the line, that means every single end of the line is a carbon atom. So by showing this, we show that there are 3 carbon atoms. Okay. Now, obviously, in the skeletal formula, we will not draw the dots out. We will just draw the lines. So it's understood that you will be able to visualize the end of every line is a carbon atom. So there are 3 carbon atoms there. Okay. Now, so where are the hydrogen? So the key thing is the skeletal formula doesn't show the CH covalent bond. So how do you work out how many hydrogens there will be? Well, we work out the number of hydrogen by knowing that each carbon atom must always form 4 bonds. So we count. The one at the end must have 3 more hydrogen in order for there to be 4 bonds around the carbon. The carbon in the middle already has 2 bonds. Therefore, it only needs 2 hydrogen atoms to be attached to it. Okay, so the skeletal formula is what you commonly see at higher levels. So now we're going to use the skeletal formula to actually represent this mechanism. Now, so if this is propane plus Cl2, right? So what is the mechanism? So we know that it follows the initiation, propagation, termination. But let's focus on propagation. So we know that in propagation, all right, the propane will react with a Cl radical. Right? Now, this potentially could go 2 ways. Why do I say could go 2 ways? Either the radical is formed at the end carbon atom, the terminal carbon, or the radical is formed in the middle carbon atom, right? So for methane, this is not a problem. For methane, it's only 1 carbon atom, so it doesn't matter, right? There's no position where the radical could be, right? But in this case, we could have both situations. Okay? So these are obviously going to result in different products, right? This one will continue if the carbon atom is at the end, the Cl will occur at the end also. If the radical is in the center, the Cl occurs in the center. This is 1 chloropropane, 2 chloropropane. So these are isomers of each other. So you can see the radical, if it's changed, if the radical is different, then you result in the formation of different products, which are isomers of each other. Okay, so obviously there must be some rule, right, to govern which product is going to be the major product. Okay. So now you're going to ask yourself, for the radical to be at the end, the terminal carbon, how many possible positions can the chlorine come in from? Remember our skeletal formula, we didn't draw the hydrogen, right? So now let's draw the hydrogen back to allow you to visualize. For the Cl to come in at the terminal position, it can substitute any one of these hydrogens in yellow, right? For the Cl to occur at the end, at the terminal position, it can substitute any one of these hydrogens at the end. How many are there? There are 6. Whereas, for the Cl to occur in the middle, it can only substitute either one of the 2 hydrogens. Meaning, simply based on probability, 6:2, meaning 3:1. This is the theoretical expected ratio. Okay, the expected ratio simply based on probability. The probability of the chlorine ending up on the terminal position occurs when it substitutes any one of the 6 terminal hydrogen atoms. Okay, whereas the one in the middle has to substitute either one of the 2 hydrogen atoms in the middle. All right, so it's 6:2, 3:1. Okay, however, life is not so straightforward. The actual ratio will be something more, okay, about, this is definitely less than 75%. This is more than 25%. So 3:1 means 75 to 25, right, percent. But the actual ratio is not like that. The actual ratio actually has less than 75%, 1-chloropropane, more than 25%, 2-chloropropane. Why? What this means is that perhaps this is a more stable radical. Okay? Perhaps when the radical occurs on the center carbon atom is more stable. Now, this is more stable because this is a secondary radical. Why is it secondary? It has 2 carbon atoms attached next to the radical, right? There's 2 carbon atoms next to the radical. So a secondary radical is more stable than a primary radical. So next to this radical, there's only 1 carbon atom. When I say next to, means immediately next to. Okay. Okay, so this is just an introduction for you to predict the ratio, the theoretical ratio versus the actual ratio. Okay, so moving forward, now we have seen free radical substitution of alkanes, learned how to draw the mechanism. Now let's move to another important mechanism, which is for alkenes. Okay, and the mechanism for alkenes is electrophilic addition, which we have actually gone through during the round 1 training. So remember, electrophilic addition is how alkenes react with hydrogen, bromine, and so on and so forth. So today, we would see the reaction of an alkene with steam. So I'm going to use propene plus steam as an example to show you the mechanism today. Now, how do we draw the skeletal formula of propene? So just now we saw skeletal formula of propane. Propane has 3 carbon. Propene also has 3 carbon because of the prefix pro. So 3 carbons is like this. But I know it's an alkene. Alkenes must have a double bond. Therefore, the skeletal formula of propene is shown like this. Okay, so that is the skeletal formula of propene, having 3 carbon atoms as well as a carbon-carbon double bond. Now we have steam next. Steam is H2O. So this one doesn't have skeletal formula. This one merely we draw the usual H2O dot and the Lewis structure, not the dot and cross, the Lewis structure. Okay, now H2O is a polar molecule. It contains OH covalent bonds, which we know are polar covalent bonds because oxygen is more electronegative than hydrogen. So oxygen has a partial negative charge. Hydrogen has a partial positive charge. Okay, so what does this mean? This now means that, hey, hydrogen probably needs and wants some electrons because oxygen has already pulled and attracted the shared pair towards oxygen itself. Hydrogen is somewhat electron deficient. So we call this an electron deficient region. So the delta plus hydrogen is an electron deficient region. On the other hand, the carbon-carbon double bond is an electron rich region. Okay, the double bond obviously is electron rich because a double bond indicates that you have 2 pairs of shared electrons, or 4 electrons in total. So what's going to happen now? Okay, what's going to happen now is that clearly the double bond has electrons. The hydrogen wants electrons. So we call this an electrophile. The thing that wants electrons is called the electrophile. So the hydrogen, the delta plus hydrogen atom, is a very good electrophile. It wants and loves electrons because it is currently electron deficient. So where will it get these electrons from? It will get it from the double bond. From double bond to hydrogen. So the arrow is from double bond, forming a bond with hydrogen. So can you see this arrow that Mr. So has just drawn? From the double bond to the hydrogen. Now you notice this arrow is a full arrow. Just now we had drawn half arrows. If it's a full arrow, what this means is that electrons are lost and gained. You do not have even splitting of the electron number anymore. So whenever you have a full arrow, you expect electrons to be lost and gained. So loss and gain of electrons obviously forms ions. So now we are going to see ions being formed in this mechanism because of the electrons being lost and gained. Now, this is not the only arrow. Hydrogen can only form 1 bond. So if hydrogen forms a bond with carbon of the alkene, the existing OH bond must also break. So there are 2 arrows in this single step. Okay, why must there be 2 arrows? Because the hydrogen forms a bond with carbon. It must break its existing bond with hydrogen, with oxygen, sorry, because hydrogen can only form 1 bond. It is unable to form more than 1 bond. So whenever you have H, you must be mindful. It can only form 1 bond. So if it forms a new bond, it has to break the existing bond. Okay, so what this ends up with is this. The double bond is gone. But now, because the electrons went away from the alkene, right? The electrons went from the double bond to hydrogen. So now there must be a positive charge. Again, we can imagine, oh, then where is the positive charge? Is the positive charge going to be at the terminal carbon or the middle carbon? Because both carbon atoms were in the double bond, right? So both of these are equally possible. So this is called the primary carbocation. This is the secondary carbocation. Carbocation means the positive charge is on carbon. As you can see here, the positive charge is on carbon. Now, besides forming the carbocation, what do you also form? Remember, okay, the hydrogen broke its existing covalent bond with oxygen. So what you are left with is the electrons went to oxygen. So that's OH minus. Okay, so you form the carbocation and OH minus ions. So that's the first step. Okay, the first step of electrophilic addition is the formation of the carbocation. Now, obviously, the second step you can imagine will involve the carbocation reacting with OH minus. Now, OH minus clearly is negatively charged, clearly is quite electron rich. So what happens is the electrons can form a bond with the carbocation's carbon, and this is what you form. Okay, obviously you have two carbocations, so there's two possibilities here. Again, you can see these are isomers of each other, right? The one on the top is called propan-1-ol, where the OH group, okay, the alcohol hydroxyl functional group is at the terminal carbon. This is called propan-1-ol. The one at the bottom is called propan-2-ol, where the OH group is in the middle carbon. So again, two isotopes, okay? Two isomers, sorry, isomers. Okay, so we have different steps here. Okay, we have the first step, which is the forming of the carbocation, and we have the second step, where the carbocation reacts with the OH minus. Obviously, these are the two steps, but they don't occur at the same speed. Which one do you think is very fast? The one that's very fast must obviously have a lower activation energy barrier. So if you look at both steps, which one do you think will have a lower activation energy barrier? Which one do you think will occur more easily and readily? So if you just analyze the two steps that we have drawn, it's quite obvious. The second step is the one that is very fast. It is very fast because it involves oppositely charged ions colliding together. Oppositely charged ions already attract each other. So for them to collide together and react is really not difficult. This attraction will allow the oppositely charged ions to collide together readily. Therefore, it has a lower activation energy for sure. So the second step, where the carbocation, the positive carbocation, reacts with the OH minus ions, this is very fast because it has a very low EA. On the other hand, the first step will definitely be slower in comparison because it involves bond breaking and bond forming, of course, between the carbon and hydrogen. All right, but this you can see, it is not a collision of oppositely charged ions. Therefore, it will not be as fast as the second step. So we say that the first step is the rate determining or the rate limiting step. The rate of the overall reaction is limited and determined by the slowest step in the mechanism. So the slowest step in this mechanism is the first step, which is the formation of the carbocation. Okay? So that will be called the rate determining or the rate limiting step. Okay, so for propene, we have seen that it forms two types of carbocation ions, the primary and the secondary carbocation ion, right? So in the first step, depending on where the positive charge is, all right, the carbocation ion will differ, and this will result in different products formed at the end of the second step. Now, so just to highlight to you, the primary carbocation ion is formed when the hydrogen is added to the middle carbon. The secondary carbocation ion is formed when the hydrogen is added to the terminal carbon atom. Now, in terms of stability, the secondary is more stable. A secondary carbocation ion is always more stable than a primary one. So the rule is, the more carbon atoms you have next to a positive charge, the more stable it would be. So a secondary carbocation ion has two carbon atoms next to the positive charge. So this makes it more stable. If it's more stable, this means it will be formed in a greater amount. Hence, you can predict propan-2-ol. Propan-2-ol will be the major product. It will be the product that is formed in a larger proportion, larger amounts than the propan-1-ol. So if you react propene with steam, you are looking at something like 80% of the product will be propan-2-ol. Only about 20% will be propan-1-ol. All right, and this is because of the stability of the secondary carbocation ion. Now, this rule has a name. This is called Markovnikov's rule, which we have gone through in round 1 of the Chemistry Olympiad training. Okay, Markovnikov's rule states that a secondary carbocation ion is more stable than a primary carbocation ion. Okay. A tertiary carbocation ion, where there are 3 carbon atoms next to the positive charge, is even more stable than a secondary one. So the more carbon atoms you have directly next to the positive charge, that will make it the carbocation ion more stable. Okay. Now, so we end up with 2 products in this case. From propene, we end up with propan-1-ol, propan-2-ol. Right? We said that propan-2-ol is the major product, but this means that you still have a little bit of propan-1-ol as an impurity. So how would you separate these two? We will have to separate the 2 isomer products using a method. And the most common method we use in organic chemistry to separate isomer products is fractional distillation. All right, so propan-1-ol and propan-2-ol, they are isomers of each other. So they have slightly different physical properties. For example, their boiling points are slightly different. Because their boiling points are different, we can use fractional distillation to separate propan-1-ol and propan-2-ol. And indeed, when you do this reaction in the lab, okay, after finishing the reaction, the next step is actually to do fractional distillation to separate these 2 products formed. When you use fractional distillation, then you will see that, oh, propan-2-ol is actually the major product because you get more propan-2-ol from the reaction. Okay? Now, so today has been a quick introduction to 2 mechanisms, namely free radical substitution of alkanes, electrophilic addition of alkenes. Okay, now the key thing in organic chemistry is to draw the mechanism and to be able to reason the mechanism out. Okay, so what do I mean by reasoning the mechanism out? Now over here, I've shown you propene plus steam. But the mechanism will also be similar if I had used propene plus HBr, for example. Because we know that bromine is more electronegative than hydrogen. So if it's HBr, the hydrogen still has delta plus, the bromine has delta minus. All right, so you should be able to draw the mechanism out if it was propene plus HBr. Okay, so can I please encourage the 3 of you in this Zoom meeting? Let's try drawing the mechanism for propene plus HBr, propene plus an interesting molecule called ICl. So ICl is a covalent molecule containing one iodine and one chlorine atom. So try drawing these mechanisms out yourself. They all follow the same mechanism, which is electrophilic addition. So try reasoning this out yourself based on where the delta plus and delta minus will be in these molecules. Okay? Can? So this will allow you to learn how to reason out an organic chemistry mechanism on your own. Okay? So if you are lost, you should always go back to the mechanism and the arrows you have drawn. All right? This will never change. The only thing that changes, of course, is the elements present in the reaction. The delta plus, delta minus can be worked out from the electronegativities of the elements involved. Okay, and remember, under electrophilic addition, we also said that a secondary carbocation ion is more stable. Okay, so that will be formed in a larger amount, resulting in a major product, a minor product formed, which needs to be separated by fractional distillation because of their different boiling points. Okay, so this brings us to the end of today's lesson. All right, tomorrow we shall continue with other reaction mechanisms. So please do look through today's reaction mechanisms and practice, internalize them, and ask me if you have any questions before tomorrow. Okay, thank you.